Welcome to Chapter 15, Inference for Regression. This is going to be a rather interesting chapter where we combine the idea of regression, aka linear regression from Chapter 4, and the ideas behind inference. So you should be thinking confidence intervals and hypothesis testing. So if you're wondering how those two are going to go together, that's exactly what we're going to get into. So I want to start this off with looking at an example because I think it'll help you build some natural intuition for this. So one of the examples from your textbook in Chapter 4, which you may or may not have looked at, was the Namblay-Mills example, where they were trying to predict the price of a product based on how much time they spent polishing the metal product. So idea being that the nicer it looks, the more likely it's to sell and all that. So if you look at this equation, you can see that it has a negative intercept. So you might be thinking like, oh, if I don't polish it, I'm not going to sell it because it's going to be negative. And then for the amount of time you spend on it in minutes, you increase the price of the product. Yeah. So what we'd like to do is we'd like to take this regression model that we have based on the sample data that we were using to make this model and take it into the next level. So if this is what the regression looks like for the sample, what can I use to say about what's going on for all possible samples, so all possible of this metal product that Namblay-Mills is making? So the idea is that we have a sample, 59 observations, and you know that if you grabbed a different sample of 59 observations, so 59 products, you would get a totally different result. You might even get a totally different equation for the regression line. So the idea is out there somewhere is the regression line for if you didn't use a sample, aka the one from the population. So I'm hoping you notice that down here in this equation below, I have a couple things floating around. For instance, oh, look, there's a true population mean, or the mean of y, based on the true population intercept and the true population proportion, or not proportion, sorry. Well, it is a proportion technically, but the true population mean. So this is like the master line that all lines should approximate well. So be thinking this is the population regression line. And since we have these three new population parameters, we actually can try to estimate all of them. And that's what inference for regression is going to be all about. Okay, so here we're using mu y to represent population mean of y given a specific value of x. And that's going to become very important as we proceed further. So if you're thinking about the Namblay-Mills example, you're thinking of a specific time and what the average sales would be for that specific time. And this value is going to change for every single x. So as you look at this, you should be thinking, oh, so I get a different line based on every single estimate I'm going to be doing. And that's exactly what's going on here. So you know, here's a bit of an image on that. So we're thinking of it as, oh, so for each specific time, so each of these specific x's, there's a range of possible values. That's why there's a distribution here. Distribution. That mean could possibly be. So be thinking like, oh, like spread, like confidence intervals. There's a lot of values that this could possibly be. And I might not necessarily see all those values based on the sample that I have. So as you look at this, we would think about the sample y's will have some distribution around the mean y, but it's not necessarily going to be exact because we're estimating here. We're using a sample to predict the population. We're inferencing. And so what we want to do is we want to look at the difference between our sample y, that guy, and the true y, the population one. So it's, again, the difference between a statistic and a parameter. And what I want to do is I want to say, oh, well, if I don't know the difference between these two, there's going to be some error term. This should be a hat, sorry. Amount it's off by. So be thinking, oh, E, I remember this. This looks like residual. This is the parameter version of residual error. Okay, so what we're going to do is we're going to collect a sample and estimate the betas, that's the name for these capital B's that you're seeing, or the B's with the tails. That's called a beta. By finding the regression line. So be thinking, oh, I'm going to gather my sample line from the data that I have, and I'm going to use that to predict the truth, the true means, the true slopes, and the true intercepts. So I'm going to be using the sample to estimate the population, the sample to estimate the population. That's exactly what's going on. And then the residuals are going to be good estimates of the epsilon, which is the name of that curly E, the all error of using the line instead of the data for the entire population. So since you're looking at these values and we're using estimates, we can actually use confidence intervals to create these estimates for these proportions, or means, depending on which one you're doing. Okay, so we know that the least squared regression line is going to give us a reasonable estimate, provided we sampled well and appropriately. And we won't be able to know exactly what the true model is, what the true parameters are. We can only estimate, and that's exactly what a confidence interval does. So our challenge is going to be, making sure that our confidence intervals are precise, so they're tight, narrow, but at the same time able to accurately estimate what we're looking for, which is the, not just precision of the event, but the probability of the event. And the idea is that we've looked at this problem before. We know that if we want to have a better representation of our true population parameter, the only way that fixes both those problems and makes sure we're precise and accurate is by increasing our sample size. So we're really going to watch our standard errors for both the slope and the intercept. And this is where this gets a little complicated, because you now have 3 different errors floating around. You have the residual error, you have the error for the standard deviation, and the error for the slope. Okay, so what we want to do is we want to, minimize the destruction that this is going to provide for us. How can I phrase this in a way that hopefully makes sense? There we go. Sorry. So what we want to do is we want to ask ourselves, how can we determine the standard deviation of this distribution for the slope? So there's going to be 3 factors that are going to make a big difference here. And the first thing is, in comparing the graph on the left to the graph on the right, we notice that one has significant amount of scatter compared to the other. And we want to make sure that, the underlying population consistently gives us the same slope. So what I'm saying is, if it's tight like this, one on the left, and I gathered a couple of these dots, so I'm specifically trying to gather dots that are in the sample. There we go. And then we did a least squared regression line for those red dots. Oh, I'd get something probably pretty close to the true line. However, in looking at the graph on the right, if I picked a sample and say I got one like, and I'm picking these so that you can see how far off this might be. This guy I probably would call an outlier, so I probably shouldn't be picking him. But so pay attention to where my red dots are. That's where I'm going to form a line. Oh my gosh, that one's not even right with slope. That's a bad sample. You might have been like Captain Magic and gathered one like this blue one I'm now putting in, and that, had a pretty close slope, but it even might be off. See, this seems too sharp, too steep. Yeah, or you might have the red line, which is like, oh my gosh, it's negative slope. That's bad. It should have been something relatively positive, because if you would have done the regression line for all the data, you probably would have gotten something like what I'm drawing in yellow. Same thing for over here on the left. So what I'm saying is, on the right, if you would have gathered a sample that happened to be not very representative, you could have accidentally gotten something that not only was maybe too steep, but even have the wrong sign for the slope. So what we want to make sure we get is that we get consistent regression slope. And this is the problem of spread that I'm demonstrating here. So as you look at this example of these 2 graphs, be thinking, oh, we want a spread that consistently gives us the same slope. And that's not always easy to acquire from your data. Next, let's look at the spread of just the x's. Here we go. So in calculating the standard error for regression slope, this is actually really going to matter. So the graph on the left, compared to the graph on the right, has a tighter spread. So I'm saying, like, just looking at the spread in the x direction, it looks like from here to here and here to here. So this one is much tighter in the x direction. Wider or whatever the opposite of toid is. I don't want to call it loose because that might make you think they're scattered out more. But I'm hoping you notice that these are over basically the same y range. Yeah, so the only thing that's difference between these two graphs is the one on the left has a tighter x range than the one on the right. And now you got to ask yourself, why is this going to matter? Well, when you're calculating slope, or B1, come on, pen, there we go. We do R sy over sx. And the issue here is we're looking at the spread of x. If your spread of x is more consistent, you have a more stable base. So as looking at the graph on the left, you don't have a wide range of possible x's there. So even if I sampled things that were super far apart, you know, that's the most they're going to be is like, you know, maybe 2, you know. So as I'm looking at what I'm dividing by, I'm not going to be significantly different from if I would have chose a sample that was in a little bit tighter, because these two are like a little bit more like 1 apart. However, if you look at the graph on the right, think about what your base could be. It could be that you get a bunch of stuff that's really close together, you know, and then your spread of your base is like a 1. Or you could get stuff that's like across the entire range, and then your spread of your base could be something as big as like a 5. And that makes a huge difference when it comes to what you're dividing by. So if your data has a huge amount of variety in what its spread of the base could be, this can also significantly affect your ability to estimate the slope well. This is the last one we're going to look at. So you're looking at these two graphs and you're thinking, oh, well, these look almost the same. They have the same range in x, same range in y, except for one has more dots than the other, and that looks to be the only difference. Hold on, I'm getting the pen to work. Oh, I'm going to have to pause. Hold on. Okay, sorry about that. So what are we investigating here? Well, we're looking at the sample size. So I don't think it's too shocking to say that, oh, when I have a larger number of dots to choose from, I am going to, you know, get a more consistent value. And the real reason I want you to think about this is to also think about the inclusion of something that's a little more unusual. I'm hoping you notice that there's 4 or 5 dots down here at the bottom. Come on, pen, I got you working a minute ago. There we go. That are a little bit less than everybody else. And they do show up in here. They're a little harder to spot because there's more data. But I want you to think about it this way. So above I have about, 30 dots and then 5 unusual guys. So my chance of getting an unusual guy is 5 in 30. That's not very good. About 1/6 of the time, I should select something that just doesn't seem to follow the rest of the pattern. But if you look at the stuff on the right, you'll notice that, oh, there's a lot more dots to choose from. So the idea is that I'm less likely to choose unusual values. I'm more likely to choose values that are more consistent towards what my regression actually looks like. This is why a bigger sample size is going to give you a more consistent estimate for the slope. And we're going to include all 3 of these ideas in trying to come up with the standard error for the regression of the slope and how each of them is going to affect the spread of the slopes. Sorry, just 1 for this. When we hit the next chapter, it's slopes because there's many of them, so sorry about that. All right, so this is what it looks like. So if you want to back up and watch the previous 3 slides, this was the first slide, and this was the second, and this was the third. So spread about the line, spread of the values of x, and then sample size. And all 3 of those contribute to what the standard error of the regression slope is, which is this equation down here. Woohoo! And so what we want to think about this is the spread around the true slope, beta 1. True slope, woohoo! And it's the error you get from using B1 to estimate the true slope. So that's what we're going to use as our spread as we build a confidence interval for our true slope beta 1. So here's how we do this. We use the central limit theorem and we use Gossett. It really shouldn't be too surprising that we're using Gossett's student t-distribution to do this because we have no idea if what we're looking at is normal or not. So I hope that's not too surprising to you if you're questioning why aren't we using the normal distribution. The T model is a much more stable model when it comes to doing inference, and so it's better to use him than accidentally use a Z when you shouldn't. So as you look at these values down below, I'm hoping some of them look familiar. This is the one we just talked about, the standard error for the slope, and then up above we have the a subtraction of the sample slope minus our estimate of the true slope. And then we use the student t model with n minus 2 degrees of freedom. So if you're thinking about, well, what sample size here, that's the number of data in your sample. So if your sample that you're looking at was the Nambley Mills sample, they had 59 measurements. So our degrees of freedom in that case would be 57. And then just a reminder for the formula for the standard error and what the in case you forgot, the spread, so this is the standard deviation of residuals, just in case you forgot what S is. And this is what, or S, because that's what Minitab calls it. Anyway, and N is the number of data values, I already said that. So this is what we're going to be using. Yay, that's my T value. I'm going to be using that to build confidence intervals and hypothesis tests. Okay, so now you're thinking, oh my gosh, what's my null going to be? Remember, null is your status quo. It's your normal operating modus. It's the idea that nothing's going on or there's nothing unusual here. And by that, we mean that, oh, well, we think, oh, come on, that, well, there's nothing going on. As in, I think, that's supposed to be a beta. It looks funny. That my slope is nothing. AKA, there's no line here, or my line is horizontal, or there's no real relationship between these two variables that has a slope of any kind. And it's really saying that, you know, the change in x and change in y do not depend on each other. There's nothing happening. So this means that y doesn't linearly change when x changes, or that they have no relationship. So this is saying that the association is completely null and void. There is nothing going on here. Yep. Were you surprised by that? Obviously, you want your slope to actually be a value so you can make a line, and that there is a relationship between them and that you can describe it. So that's, you know, what the alternative looks like. But remember, the null hypothesis is always about standard operating procedure, nothing going on, hence the name null. So it's assuming your slope is nothing. Yay! So this is what that test is going to look like and what the confidence interval is going to look like. And remember, this confidence interval is for the regression slope, not for anything else. We're going to run into something a little bit later called a prediction interval, and that's a little bit different. And we want to be careful with that. And I want you to notice that, and I'm going to highlight this so you can see it a little bit clearer, our null hypotheses and our alternative hypotheses are always the same, or possibly a one-sided alternative. The big thing here is that our null is always the same. It's always, I assume this is nothing. So be careful with that. And then we use the following test statistic and the T model with the degrees of freedom and n minus 2. If you're wondering why it's minus 2, it has to do with the fact that you're doing things in 2 dimensions, not the fact that you're doing things in 1 dimension. Previously, when we've done hypothesis testing with degrees of freedom like this, we've been looking at the interaction with 1 variable, and we just do n minus 1 to account for its presence of the mean. And here, since we're dealing with 2 variables, an x and a y, we have to account for the presence of both means, so we're subtracting 2 instead of just 1. Anyway, and we look at p-values, so no big deal. Now, below that, I have the formula for the confidence interval. Yay! Oh boy. Sorry, I'm yawning up a storm today. So, again, this isn't anything too surprising. We have the sample slope plus or minus the t following the same degrees of freedom times your standard error for the slope. Woohoo! All right, so here's a look at what this looks like. This gets a little complicated. So this is the kind of thing that Minitab would give you an output on for doing linear regression. And we have had this as our output before in chapter 4, and you saw it in stat 1. But you never really paid any attention to this part of the output where it was like, oh, list the variable and what's the coefficient and da-da-da-da-da-da. Anyway, so we're going to go through that. I'm going to show you how to use this to do a test. So here's an example involving soap. Woohoo! So a soap manufacturer tests a bar of soap to see how long it would last. The test subject showers each day for 15 days and records the weight in grams of the remaining conditions. Remaining conditions were met, so linear regression gave the following. So as you look at this, this is a little bit of a silly thing, but I used to actually use this as a stat 1 project of making people use soap to tell what's going on. Yeah, so anyway, let's get into this. So you should see some things that you recognize on here, like r squared. That's a concept from chapter 4. But I want you to notice that present right here is the standard error for, oh, that's illegible. Hold on. standard error, that's the SE, or the value for the error of the residuals. And there's some other values here as well. So in particular, your coefficients, let's highlight part of this, highlighter green. So going and reading down, come on highlighter, there we go. Reading down this first row here, this is the stuff for the intercept, and that's a little bit interesting, I hope, to you. Okay, so the stuff for the intercept is, a little bit different from the stuff for the slope. We're not really interested in that, but I want you to notice that there's the standard deviation. This would be the standard error for B0, or the intercept. This would be the coefficient for the intercept, so that's actually the value of B0. And then just below that, we have all the stuff about day, which is the variable that we're interested in. So the value right below that, the negative 5.5747, that value is actually B1. And then right next to it, we have the value of the standard error of B1. And then we have the t ratio, or the test statistic, right next to it. So that's that t we were just talking about. And then we have the p-value for the slope. So this is all the stuff we need to be able to say, is the slope significant? So we're going to use all that to answer these questions. So be careful when you're reading this to break up the pieces and make sure that they make sense to you. So the first thing I ask you is, what's the standard deviation of the residuals? That's the yellow thing I labeled. Okay, what's the standard error of B1? It's one of the red things I labeled. I should have did different colors there. And what are the hypothesis tests to the slope? Is it medial? And then we'll write ourselves a conclusion. So let's go through those answers now that we've labeled written all over our notes so that we know what's going on. Woohoo! So just like we saw, the standard error for the residuals is right here, and then the standard error for slope is located right here. When we get more variables involved, you'll just read down the column to find the variable that it goes with. All right, and remember our null and alternative. Well, our null is always equal to, since there's nothing in here that we have describing in the example that indicates if we want it to be greater than or less than, we go with not equal to for alternative. This is that choice right there. Let's proceed with the test. Woohoo! So here's the thing. We're looking at this p, the one going with the slope, when we're making this determination. And it's super small. So, we're going to go ahead and reject the null hypothesis. And that's good, because remember, the null was that we think the slope is 0. So clearly the slope is not 0. In fact, the evidence seems to point to the fact that it's, not 0. I just said that. Oh my gosh, I'm repeating myself. Anyway. And so you can conclude there is a linear relationship between day and weight. So all this is saying is that it appears a relationship between you showering and using your soap affects the weight of the soap bar, which isn't too shocking. Anyway. So what we're going to do next is we're going to find a 95% confidence interval for the slope, and then we're going to interpret it, and then use that to come up with a answer to the null hypothesis idea. So we're going to see if 0 is in there, basically, for the same example. So we're going to be using all the pieces we just had to try to answer the question of, oh, do I get the same results if I would have used a confidence interval instead? Okay, so setting this up. If you're wondering how I got my t-star, I have a video on how to calculate t's that I think I'm going to link to again. I had it show up earlier, but I think I'll do that again as well, just in case people forgot it. Anyway, so we're just plugging and chugging here. We're throwing in our slope, our standard error, getting our t, throwing it in there, and then adding and subtracting the values after we multiply to make sure, sorry, we multiply this first. And then we add it and subtract it to the B0 value, and we come up with something that's completely negative. And that's what we wanted to see, because we either want it to be completely negative or completely positive, because that definitely indicates that 0 is not in there, and therefore we must have something that is significant when it comes to our slope. All right, so let's interpret this confidence interval. We can be 95% confident that the weight of soap decreases by between 5.34 and 5.8 grams per day on average. So be careful when you're writing these conclusions in particular. So when you're looking at concluding something about a slope, you are estimating the slope. So you need to make sure you're using the interpretations of the slope to do this. What do I mean by that? Well, it's decreasing because these were always negative, and then we talk about what it changes by. So like this is a definite interpretation of what is going on for this. So it's grams per day because we're looking at change in Y over change in X, and our Y variable was the weight of the soap, and that's why it's in grams, and over time, which was in days. So that's got to be in there somewhere. You need that description of how it's decreasing. And you need to mention the fact that it's an average. So that's the last thing you need to be careful about and make sure that you include is that average word, because this is estimating an average. Alrighty, not a proportion. Be careful. All right. Lastly, hey, would we get the same conclusion? Absolutely. And I said this a couple times, but since 0 wasn't in our interval, we definitely can reject. If 0 had been in that interval, we wouldn't be able to reject. We could say, oh, it's possible that there is no relationship between weight and day as far as this soap is concerned, in which case, who be not showering? I mean, oh, that was bad English. Who amongst ye is not showering and therefore causing this to be, oh, okay, never mind. That's kind of horrible. Okay. Yep. All right. I know this is confusing because it took me 20 minutes to get through 5.1. Hey, welcome to 5.2. We should check these conditions before we do any inference for regression. These should not be all that surprising. They're the same kinds of assumptions that we needed to do linear regression, and it's a combination with the ones that we needed to be able to do confidence intervals. So we need linearity because, well, we're doing linear regression. We need these to be independent because that was a part of both of them. We need equal variance, which might be one that's a little bit surprising to you. The real reason why this one is present is to keep consistency amongst your different samples. If you're a little bit confused about that one, maybe I could do something with that. Let me think. There's not a real good natural way to describe why that one is going to be what it is. I know why we need this. Okay, so we need equal variance because we need normal population assumption. These two are related, so 4 and 3 are related. And the really reason we need that is we actually need the assumption of what's called homeostaticity, which is a word I have a really hard time saying. Homeostaticity. It's a word you don't need to know. And it's basically the idea when we look at the residual plots that this is going to be consistent in as far as standard deviation is going. So we want a consistent shape that's actually something appropriate to use t and the confidence intervals on. So you should expect nearly normal to be showing up in here somewhere. So there we go. All right, so to check linearity, well, look at the scatter plot. How do you check independence? Look for randomization. That's usually our go-to for that. You also should look at the residual to make sure you don't have any weird patterns or clumps or fans or anything that might be indicating that you've got a relationship that you didn't account for when it comes to independence or dependence between your variables. Equal variance assumption. This is the same as checking the equal spread condition, which I think I mentioned a couple slides ago, but hopefully you remember that. Anyway, so what you want to do is you want to look at the residual plot and look for a consistency amongst your spread. If you don't have one, like if you have any type of shape like a fan, you're in trouble. All right. The normal population assumption. So this is really assuming that the regression line around each x is relatively normal. So think of that graph that I showed you that had a bunch of normal distributions on it. And this really is where we need to check nearly normal. So we should be looking to see, do our populations look relatively normal? Not population, our sample. We won't have the population. Sorry. Ooh, sorry. Recording in the morning, tired. Okay. The other thing you should be sure to do is to check the outlier condition. Although it's not really listed in any of the previous, if you have an outlier, you already know that when it comes to linear regression, it's going to significantly pull your data in a wrong direction. Alrighty, so summary of assumptions. There's a lot of these. So make sure you're checking all of these out. I would say when it comes to your notes, maybe write these down and or star or circle this slide. That way you come back and look at it when it comes to performing your regressions to make sure that you actually account for all of these. It's basically just a summary of what I just said. Hello and welcome to the weird section. It used to be that if we were looking to see if there was a relationship between two variables that were quantitative, we would do what's called a hypothesis test for correlation. So we'd start out with the assumption of, oh, the correlation is zero, aka there's no association, there's no relationship between these two variables, and we would test that. Usually our null would be it's zero, and then our alternative would be it's not. And this sort of fell out of favor in favor of the slope model because it makes a little bit more sense, and these are equivalent because remember the equation for slope is, r sy sx. And if you think about it, if slope is zero, then, one of these has to be zero. And it can't be sx because if it's zero, you just violated the laws of mathematics and you just divide it by zero, you put a hole in the universe. We're not going to do that. So it's not that one. And if sy was zero, well, then we wouldn't be looking at this at all because then we'd have no spread amongst the y's and we'd actually have what's called if the y's aren't spread, that'd be a horizontal line, in which case, my slope would be zero anyway, and you're good because, if my slope is zero, then my spread is zero, and we're done. And that's kind of obvious. So it has to be that the correlation was zero. And then alternatively, you could ask yourself, well, what's going to happen if correlation was zero? Well, then I'd have a zero right here. And then it doesn't matter what sy and sx are because you're multiplying by zero, and then b1 would have been zero anyway. So this is the equivalent test. If you don't care about the algebra behind this, that's okay. So what it's really saying is that, oh, we do b1 instead. They say the same thing because trying to determine if b is zero is the same as trying to determine if r is zero. Okay. Whew. This is the t-test for that test. So as you look here, you'll notice this funky looking p. That's called rho. Rho is the Greek letter we use to for correlation of the population. So we'd say that R estimates rho. So you'll see R showing up in this equation. So your sample correlation estimates the population correlation. The population correlation we call rho. This is like the same test. I hope you're realizing that because it's still a student T model. I'm still doing n-2. It's just you're testing R instead of testing B1. We almost never do this. All right. Things to look out for. Hey, you're business people, in case you forgot. Well, most of you. When you're doing predicted responses for y, you have to be given some value for x. Remember, these are just your best guess. They're estimates. You want to estimate things like your quarterly losses or your quarterly gains. There's like some different ways you could possibly do this. And we've so far done it on doing lots of averages. I think the average is going to be this. The average is great, but it doesn't tell you a range of possibilities. So I might tell you something like, oh, the average amount of spending for this department is like $200, and that's useful because typically it looks like $200, but there could be a lot of different values that could come out of that department. It'd be more useful sometimes to say like, oh yes, the average is $200, but the range of possible values is between $0 and $2,000, and you're able to predict a worst case scenario then by saying things like, oh, well, I know it could be up to this much. I should prepare for that possibility. And if you furthermore know that it looks normal, you can say, oh, like 68% of the time it'll be between this and this around $200. So usually it's like between 100 and like something else. So it's just a different way of estimating and predicting. Let's take a look at this. Woohoo! So the standard way we've done this is given a single x value, we find a confidence interval for the predicted mean. So this is the one we've done in the past. And then the other one we're going to learn to do is we can look at a given x value, we can give a prediction interval for all the values of y. So we're predicting all the possible outputs you could get from that particular x. So just like I was saying with the department spending, it could be $200 on average, but the range of possible values that all could possibly be might be between $0 and $2,000. It's quite a big deal. And we're going to use Minitab to produce these prediction intervals, and it's actually really easy to do. Let's take a look at what they look like. Okay, so this is the formula for the confidence interval predicted mean value. This is gross. I'm going to not make you do these by hand because they're gross. So be prepared for that fact. But here's the formula in case you ever need it. So you have to have the predicted mean first. So you have some prediction of what you think the mean is going to be, and you have this X value you're interested in and putting in there. And then you use this to calculate your spread for all possible values. If you're wondering where this n plus 2 comes from, that's actually coming from the exact estimator off of a binomial. It's super weird. There is no good way to explain this formula to you. I am sorry. But you should look at, it's about estimating like what the spread looks like when I compare my mean in my sample to all the possible values. So this is definitely looking a little bit like a standard deviation, but not completely. And with this last term in it, it's trying to account for all possible residuals, because notice it's including SC, which is the standard error for the residuals, or your spread of residuals. So it's not only trying to account for all possible values, but just how spread they might be from their standard values. This is a complicated formula. Alrighty. So we use this to form the prediction intervals using critical value T star. This doesn't look like anything different from the last slide, and I don't know why it's in here. Moving forward. All right, let's look at the non-blame bills example and form ourselves a prediction interval. So this is that previous, just the previous equation from the non-blame Mills example based on time and price for polishing. And what we want to do is we want to look at the two different intervals that we can now create for a item that we're going to polish for 25 minutes. So as you're looking at this, come on, 25 is going to be taking the place of my X value of interest. All right. So if we just use the standard formulas we have from before to calculate the confidence interval for the mean, so be thinking this is just a simple T, the 95% confidence interval for the mean price of items is that it's between $90.20 and $110.06. So we are 95% confident that for all items that we polish for 25 minutes, the above interval contains the true mean sales item price. So again, this is the mean. Be careful. These are about means. These are about means, not about individual prices or about all the possible prices. This is what I think the mean looks like. It's somewhere between these two. Come on. Okay. Now, if you form the prediction interval, so using those formulas I just showed you 2 slides ago, you actually get between $34.22 and $116.04. So this interval is super wide. Why is it so wide? Because it's not like what's going on for a single It's not what's going on for a single item that you're trying to sell. It's going for all the possible values you could see for all the possible items. And you really need to be careful when trying to use this to say what's going on. So 25-minute polishing time, you're 95% sure that the price of the randomly selected item is between these two. So again, this is all possible prices, not just the mean price. It's not the average, it's the list of all possibles. It's 95% of the time going to be this. And it's super wide, so it's not very precise at all. Okay, so let's look at another example, and we're going to actually physically calculate these now that we know how to use and interpret them, which is what the last example was about. Okay, so we're going to look at external hard disks and their price based on their capacity. This is some interesting data, especially since historically price tends to go down over time when it comes to capacity as capacity increases. If you've ever bought a external hard drive or any type of hard drive in the last year or so, it's much cheaper than it was 5-10 years ago. All right, so here's our equation. I've given you the standard error for the residuals, the standard error for slope, and the mean of the sample, as well as, and be careful, this is the mean of the X, so this is the mean for capacity. So this is, this is in gigabytes. I should have written that in there. Anyway, and my sample size was 7. This is not a big sample, so you should be expecting this to be, a little bit tight on the results. Anyhow. So we're going to find the predicted price for a 1000 gigabyte hard drive. We'll find the 95% confidence interval for the mean price then, and then we will find the 95% prediction interval for a 1000 gigabyte hard drive. So we're doing two things. We're finding the price, the mean price for 1000, and what we think the all possible prices for 1000 gigabyte is going to be. And here's how you start doing that. So the first thing we need is we need the predicted value. So all we're doing is we're taking the value that I'm interested in and substituting it into the equation and getting a value. And we notice that it's $122.64 as the predicted value for that. All right. Next up, we're going to form the confidence interval using the following formula. So I'm hoping you notice that there's a couple things going on here. I've got my standard error showing up. I've got my difference between my predicted value and the mean. I've got my standard error for the slope. I've got my t-value. Be careful as you look at this. Since n is 7, my degrees of freedom is 5 because I'm subtracting 2, 1 for each mean. And then my average for y, that's my predicted value from before. That's that 122.64 that we just calculated. And then we just need to plug and chug away, woohoo! And we get a range of $105.14 to $140.14. We are rounding this way because this is money. All right. Now what we want to do is we want to form the prediction interval. Remember, the prediction interval is slightly different, and it wants to account for all possible values that you could be encountering. So there's a couple different terms that are extra in here, such as using the standard error multiple times to account for spread in either direction. My caution to you when calculating this is to be very careful and to not round until you reach the end. And so we arrive at the prediction interval of $73.28 and $172. If you cannot get these values using the calculator you currently have, I would highly suggest you go watch my video on how to download and install a TI-83 calculator for free onto your computer so that you have a more advanced calculator that is capable of handling these type of calculations without difficulty. If you need help using your calculator and entering things into your calculator, please do not be afraid to contact me. I am more than willing to help you. Yay. All right, that's it. So, what can go wrong? So much. This is complicated. Don't try this on things that aren't straight. Watch out for spread. These are not too surprising because we're still talking about linear things. Watch out for non-normal errors, aka you should always check for normality in your histograms. Be careful with your p-values, especially on two-tails. They're, I know I did a bunch of two-tails because they're the typical for these, but watch out for one-valued or one-tailed ones because they do happen where they think things are greater or smaller. All right, so what have we learned? Hey, these are the things I know, woohoo. We know the assumptions and conditions. We know we should be using a student t for this. I know what my residuals are and my standard error and sample size. These are all the things you should watch out for when you're calculating your slope coefficient, and they all affect it. All right, lastly, here's the standard error for the slope, the one that's affected by those three I just mentioned. Ooh, words. A standard error for the slope, remember, it's an estimate for the population standard deviation for the sampling distribution of the slope. These are still sampling distributions. So we've combined sampling distributions into linear regression. I hope this is blowing your mind because it blew mine the first time I saw it. I hope it's not actually blowing your mind. Anyway, remember when we're looking at our null, it's always a statement that I think the slope is 0, not that I think the slope is 4 or anything else otherwise value-wise. It's always we think it's 0. So when you're doing that, your test statistic always looks the same. Yay. All right. When it comes to constructing and interpreting the confidence interval for the mean, in general, understanding what this value is difficult to understand. However, we can express for a specific value the mean price or the mean expected value for that prediction value. Additionally, we can look at all the possible values when we construct the predicted interval, which is the other name for this. for a specific value. So be thinking back to that very first image I showed you where I had the line and I had the normal curves on it. One of the things we're doing, which is the previous slide, is trying to predict where the center of that curve is. The other one is trying to predict the range of the curve. This is the one trying to do the range, not the mean. So I'm trying to do center, I'm trying to do spread. I'm trying to describe what this looks like for a particular x value.